So today I'm gonna just give a few uh, thoughts on something that Mike and I are working on. That's a piece of the larger operational semantics and logical form idea. Um, this was kind of folklore uh, by the mid 2000s, but nobody wrote it down at the general level. There was a result from Lawvere and Kyres that carried it out for a specific theory, but not for all Lawvere theories. So we're basically just taking their idea and carrying it out for a larger group of theories. So the background to this is, as I've said many times, bisimulation underlies all the different notions of equivalence for computation that have been put forward, right? So even for lambda, there's a form of bisimulation, applicative bisimulation that captures the semantics that you want. So and one of the things that's really interesting is the relationship between the logics, logical equivalence, and bisimulation. Milner proves that bisimulation coincides with logical equivalence or the Hennessy-Milner logics, and that's interesting, and seems to put us on the right footing, right? So logic isn't any different than any of these other proposals for a notion of equivalence, right? They coincide, and that's great. And then along comes Kyres, and he shows that that the spatial logics can see more than bisimulation. So in particular, one of the things that they see is the form. All right, they can, like, bisimulation cannot detect between par and interleaving. So given the interleaving semantics of the pi calculus, right? So if you have send on x, or let's say listen on x for y, and then listen on. Let me put it in alphabetical order. So listen on U for V, and then listen on X for Y. That's and then your summation is listen on X for Y, and then listen on U for V. Right. So if you sum those two processes, that bisimulation can't tell the difference between that. So listening in either order. Versus listen on X for Y in parallel with listen on U for V, right? So if you had true concurrency, then those two could grab two threads and run at exactly the same time. So your bisimulation would have to adjust to this idea of having multiple threads rather than interleaving. But as long as you have, only one thread, and so you have to pick an order, bisimulation can't see the difference between the par and the summation. Does that make sense so far?
Yes.
Okay, great. So then along comes spatial logic, and it can see when a program has a par in it. And so that breaks the relationship between logical equivalence and bisimulation. And then Kyres and Lawvere go back and restore it. And what they show is that if you added actions for commutation and association, then So in other words, you have a context in which you have to place the process before you can switch the order of things. Then you can go back and recover that equivalence. And if you think about it, this idea of a relationship between form and behavior, structure and behavior, is as old as computing. Right? There's a close relationship between any data structure that we might cook up, graphs, trees, bags, what have you, and the control structure necessary to navigate such a data structure. Right? Everybody knows that when you are handed a data structure, you have to pick it apart. You have to go access the data inside it. And there's this relationship between the control flow needed to go and access the data and the form of the structure itself. So essentially, this bisimulation result is akin to that understanding that virtually every programmer has. Now, does that make sense?
Yes, and these operations, these control operations can include multiple operations in the underlying structure.
That's correct. Yes, that's correct. So, so what we'd like to do is we'd like to lift this idea to the operational semantics and logical form, just for plain old Lawvere theories, right? So before we add any fancy rewrite semantics on top of the Lawvere theories, we'd like to be able to recover this idea. So we can run Christian's version of the structural part of the algorithm for any plain old Lawvere theory, and we'll get some formula, we'll get some types that have a that give rise to a particular logical equivalence. And so now the question is, what's that logical equivalence? How is that related to some notion of bisimulation? Well, in the case of a plain old Lawvere theory, we don't have any behavior lying around, or do we? Right. So let me give an example of a plain old Lawvere theory, our favorite, which is monoids. So plain old Lawvere theory comes with sorts like M for the for the elements of the monoid. It comes with function symbols like the identity E and the multiplication star. And then it comes with some equations like, that the identity serves as an identity for the multiplication, and the multiplication is associative. All of that should be bread and butter, but just want to check in and make sure that all of that makes sense. I've written that down on the screen. That's what's showing. Hopefully this makes sense.
Yes.
Okay, so then the next thing we want to do is to turn this into a graph theory. So we're going to add a sort for edges, and we're going to replace all of the information about the equations with a treatment of the edges in the graph. So we're going to turn all the equations into bi-directional rewrites. Right, so we're going to be able to rewrite a term that's E star M to an M, and also be able to turn any term M into E star M, and so on and so forth. So go ahead.
Is it similar relationship between a monoid and group? So monoid with equation inverse is the same as group, and we can see this in two different ways.
I mean, there's a family resemblance, but what we're really doing is we're 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 not we're not making it equational. We're saying that there's a computational step to go from E star M to E. That there's some compute involved. You have to rewrite the term. Okay. So we're not
So we,
turning a monoid into a group. We're turning a monoid into a graph.
so we want to get rid of equations and convert it in this format.
That's right. We're getting rid of the equations and turning it into rewrites.
Okay.
Right. And this is like if you, there are systems like this, like mod, for example, is a language that supports this kind of computation. There are other rewrite systems that provide this kind of support. So we're gonna introduce a sort for edges. So that's E. We're gonna add some function symbols, S and T, for source and target. And we're going to replace all of the equations with function symbols. So there's a star left that takes an edge and an element of the monoid and produces an edge. There's a star right, which takes a, so multiplication on the left, multiplication on the right, and then one that takes two edges. So we call it LR. And then we're going to have resources. Oh, I'm sorry. For the plane theory, we're not going to do that. Resources, so association, left and right identity, and then we'll use Greek functions to talk about the associator and the left and right identities. Okay, so the association rewrites and the left and right rewrites. All right, so then that becomes so the source. So we want to talk about the source of alpha of XYZ is going to be A XYZ, and the target is, so this is specifying the rewrite. The target of alpha XYZ is going to flip the way we've associated it, right? The source of lambda of X is going to be, we have to have an L and multiplying E on the left times X, and the target gets rid of the E and gets rid of this L gadget. And similarly for the right side. So do you understand how these two equations, the source and target equations, correspond to the rewrites? Does that make sense?
Are these like new ways how we can combine two elements of this monoid?
No, this is literally capturing the equation information. So what we're insisting is that you have to tell us when you're going to associate, when you're going to reassociate. So if you have some term, say X, and then multiply X by the thing that you get from having multiplied Y times Z, right? So the parens go around that YZ first, and then around the X times that, okay? Now, if you want to reassociate that, you have to use one of these A symbols, right? So an A resource. And if you have something like this, it will reassociate the parens, right? So think of this as a rewrite. So this is the source of the arrow. This is the target of the arrow, right? So we're taking a term like this to a term like this. And what it's done is it's shifted the parens, just like in the equation for the monoid, right? Here's the equation for the monoid. But we're turning this equation for the monoid into a rewrite. Does that make sense?
I'm not completely sure. Can you give us an example of source and target of this rewrite in some simple?
Yes, that's what I just did. That's exactly what I did. Right. So here's a. Let me do it in Emacs. I'll do it as. Okay. All right. So here's a standard association. Okay, right? That's standard monoid association. And what we want to do is we want to turn this into an arrow like this and another arrow that goes the other way. Okay, so every equation is going to give rise to two arrows, going from left to right and going from right to left. Okay?
So when we...
But we want to not have it bounce back and forth, right? So if we just had the equations like this, it would go in a cycle, right? Because we get from here to here, and then we'd apply this arrow and go from here to here, and so on. Round and around and around we go. Yes?
Yes.
Okay, great. So to prevent that, we say you don't get to rewrite any old term. You have to have an associator action. So we're gonna do this. Okay, so we're allowed to take A of something. Right, that's a new symbol. All right, and as long as I have an A, I'm allowed to go this direction. Right, but once I've gone this direction, I don't have an A anymore. Likewise, if I have an A, I can go this direction. And once I've gone this direction, I don't have an A anymore, so I'm done. I've stopped.
Okay.
All right. So if I were to calculate the source of this arrow, it would be the left-hand side. And if I were to calculate the target of this arrow, it would be the right-hand side. So let's go and look. The source of the arrow is A, X, Y, Z, right? A, M1 times M2 times M3, yeah? Right, so X is equal to M1, Y is equal to M2, and Z is equal to M3. Does that make sense?
Yes.
Okay, great. And then the target is the reassociated one. Target is the reassociated one.
What is not clear to me is what kind of rewrite we are doing here, or we are just packaging this in A to be something for rewrite.
No, the rewrite gets rid of the A and changes the association.
It's the arrow itself, right? From A to this is the rewrite.
Yeah, we're taking this term here. So here's the term, right? Together with the A, and we're turning it into this new term where you do the multiplication of M1 times M2 first, and then you multiply by 3, by M3. Yeah, so that's the change.
Hey, basically, it sounds like the point of saying A of this is to say that this transformation occurs once.
That's correct.
Okay.
And we are not using the multiplication of monoid here. We are just transforming this associativity thing as our rewrite.
Well, we are implicitly using the multiplication of the monoid. This parenthesis says this multiplication happens first, and then this multiplication happens. And this parenthesis says, no, this multiplication happens first, and then this multiplication happens.
So we have additional structure in which we can observe which order of this multiplication is will happen with this A. What you said on the beginning.
Right. We have, I mean, one way to think about this is as syntax trees, right? So these are not actual multiplications. These are multiplication expressions. So we build a syntax tree, right? Let's see. Do I have a? Oh, I can draw a graph over here. Oh, I see.
And in some language, maybe we can decide that this is completely the same, and we can erase this on one level of our rewrite.
Right. So essentially, oops. Let's try this again. So here I have a star, right? And here I have a star. And, you know, here, oh, let me do it this way. And then over here, I have an M1, right? And then down here, I have M2s and M3s, right? So that's, and then if I do our connections, let's see. All right. All right, so all right, so we have a tree like this. It's a syntax tree, right? And then we have another tree that runs the other way. So, so here we do the M2 and the M3 first, and in the other one, we're going to do the M2, the M1 and the M2, and then, so I'm just trying to think about the easiest way to do this. There you go. So that's 1, that's 2, and that's 3. Okay, all right. And so the normal equation says I get to erase these syntactic differences, right? That's what this thing says, right? So this theory builds up syntactic gadgets, right? It builds up these trees, and this equation here says that I can't tell these two trees apart. It doesn't tell me what the multiplication does. It just says that I can't make a distinction between these two trees. Does that make sense?
Yes, totally.
Okay, all right. And now what we're saying is, in order to get from a tree like this to a tree like this, we actually have to have a tree like this. Does that make sense?
Oh, wow, yeah.
Right. And so, and
Yes.
rather than getting an equation which erases differences, we have a computation which rewrites the trees. So just.
So our A is like new constructor that we added for this purpose.
Yeah, exactly. Yeah. So there's our rewrite.
So you said that in rewrite we usually forgot something.
Yeah, so we got rid of the A, and we got rid of and we shifted where the structure of the tree. No,
Can you also say that?
It's not always the case that you forget something. So notice that we'll also have the ability to go the other way. We'll have bi-directional rewrites. So if you were to put an A on top of this tree, we have another one which will run the other way, basically. Right. So if you had an A on top of this tree, then you could go to this tree.
I see. And are we creating some kind of ordering in this way?
Some kind of ordering. What do you mean by that?
Because we are recognizing these two different trees.
Yes.
And we can go from other.
Yes, that's exactly right. So what really happens is, the trees give you the information about the order of term formation, right? So here we have, let me do it this way. Okay. So in the old way, that wasn't an so this is really, it's not a rewrite. It's saying that these two are the same. So oh, it did give me the ability. Okay. So it's erasing any distinction, right? These two are the same. And in this one, right, they're not the same. We have a rewrite from here to here, which gets rid of the A, and we have a rewrite. If we were to put the A on top of this one, we have a rewrite from here to here, getting rid of the A, right? So this is an erasure of term history formation, right? So first I formed this term, and then I formed this term, right? And this is changing the order of term formation. No, first I formed this term, and then I formed that term. And this equation says, I can't see that history. This one says, oh no, I can see the history. And if I want to change the history, I have to have an A that allows me to change the history. Does that make sense?
Yes, yes, totally, totally. Yeah.
Okay. So then we can put back all the bisimulation information, right? We can treat these rewrites as you know, rewrites in a bisimulation relation. Okay, and so then we can look at the bisimulation equivalence classes. And over here in the equation, in the plain old Lawvere theory that isn't a graph theory, it's just a plain old Lawvere theory, we can look at the logical equivalence classes. And so what we're working on proving right now is that there's a one-to-one correspondence between the logical equivalence classes for this plain old Lawvere theory and the bisimulation equivalence classes for this graph theory. So we're building up maps so that if you hand me an equivalence class of from the logical side, I can hand you an equivalence class for the bisimulation side. If you hand me an equivalence class for the bisimulation side, I can hand you an equivalence class for the logical side. Does that make sense?
Yeah, yeah. Although understanding completely, it's not easy.
Sure, sure. That makes sense. But essentially, what we're doing is we're recovering the relationship between structure and function, right? So we want our logic to coincide with our behavior. That's the idea. Just we don't want there to be this big gap between what the logic can tell us and what the behavior can tell us. Does that make sense?
Can you say, for example, for monoid, the logic, the logical part comes from operational structure, right? Like a set union, or right?
Yeah. So sure, but let's think about it this way. Over here. So this is very useful to have this discussion. Okay, so we're going to have a logic, and it's going to have a few things in it, right? So a formula, let's say, a formula phi is going to have a few things. So it's going to have true. That's normal. It's going to have conjunction. So let's say phi and. Now, since I want to distinguish the two phis, I'll put a C in here, but now I don't have a C on the left-hand side. So just for grins, I'll let phi and C both range over formulae, right? So I've just given myself the luxury of having two variables over here that can be bound over here. Okay, and I can also do the unary. I can also do for grins and giggles, let's just do implication. So rather than have And instead of doing true, just for fun, I'll do false. Okay, and then this one is going to be this guy, implication. Okay, so now we've got a little intuitionistic logic, right? So what we get out of Topos theory, right? There's more to the logic than that, but that's the rough idea. But that's just the Topos part. We're also going to get, in addition to the, oops, looks like, yeah. Sorry about that. There we are. We're also going to get E. We're going to have a logical operator for E. So I can detect when something is the identity. All right. And I'm also going to have a logical operator for multiplication. I can detect when things are multiplied. So, and Ladle generates this from, sorry, put this on the wrong page. So the operational semantics in logical form generates this gadget. Does that make sense?
Yes, so far.
Okay, great. So now what we want is, notice that this logical operator, which can detect when a term has a multiplication in it, that if our multiplication, if I were to interpret multiplication as par and 0 as the identity, right? So that's a perfectly reasonable monoid, right? My monoids are all process terms, and the multiplication is par, which is associative, so it satisfies that. And 0 is the identity, so it satisfies that. So, you know, par and 0 is a perfectly reasonable monoid. Now, this thing can detect pars, right? But bisimulation can't see pars. We talked about that. Does that make sense?
Why are you saying that bisimulation cannot see par if we are not care about?
It can't see the difference between a sum and a par. A sum of all the possible interleavings in a par. Bisimulation thinks that.
I mean, we don't care about that in Rolling. So why we need for bisimulation to see this difference?
Hang on. What happened? So confused. Why did it change fonts on me? Okay. So for y from x 0 par for u from v 0. Okay, so this is a, hang on, I'm just gonna switch it around so that it's in alphabetical order. Okay, so there we go. There's that one. And now, if we look at this one, oops, plus this one. I'm going to put the plus on the second line and change these around. I've screwed this up. It should be D from U. Okay, so now the important thing is that bisimulation can't see the difference, right? So let's see, I think I have this in my favorites. No, I don't. Okay, math symbols. Here we are. Add to favorites. Okay, these two things are bisimilar. However, intriguingly, look at this. This one satisfies, hang on a second, should have it. There it is. Add to favorites.
But in the top case, we didn't have any com event.
So, but notice, it doesn't. What will happen is, it can have the comma events in either order, and this can have the comma events in either order. So if you put this in any context where you supply a U bang and an X bang, right? It will be it will behave exactly the same as if you did this. That's the important thing. But notice that this thing is logically equivalent, right? It satisfies this formula. Where just for, I'll put true here. And I'll put true here. Okay, so this is a formula that we get from operational semantics and logical form, but lo and behold, right, this thing doesn't satisfy that formula because this thing has no par in it. Okay, so now we have a distinction between bisimulation and logical equivalence. That was the point I was trying to draw, right?
Okay, now it makes much more sense. Yes, thanks.
Sure. Okay, cool. So then is this logic more discriminating than bisimulation? Well, no, it isn't if you give bisimulation the information about the structure. So we put all the information about the structure back in. We teach bisimulation about the multiplication, right? And we teach bisimulation about reassociating, right? That's what this is. This is teaching bisimulation about reassociating. And this one is teaching bisimulation about the identity behavior. And once bisimulation learns about these new categories of behavior, then it sees the same things that the logic sees. That's the idea. Does that make sense?
Yes, yes.
Cool, right. Yeah, it's fascinating to me because this has been folklore for a long time, right? A lot of people have known this. I'm not the only person that knew this. But this folklore gets lost, right? Nobody nobody writes it down. And in particular, nobody writes it down in the setting of, category theory, where its general import can be seen. Now, so there's some interesting things that have to go on. For example, you need to talk about the coherence of the combined equations, right? So you wanna look at how source and target relate to the composite of the associators and the identities, for example. So there's lots of little subtleties that are actually interesting from a category theoretic perspective. So that's really fascinating to me. And I believe that there's a lot here that speaks to how category theory and computation are still not perfectly meshed against each other. You need some kind of impedance mismatch. Like even explaining this structure-function relationship, it takes a while to get it. It takes a while to see what's going on and why it's important, why it's worthy of attention. Right? If we were doing entirely symbolic computation, you would see this immediately, right? Erasing this structure is not something you can do with a computer easily. You're going to have to implement it this way unless you turn this symbolic representation into something that already enjoys this kind of thing. And that's exactly what we do with RSpace, just so that you're clear, right? We don't have an entirely symbolic representation of the computation. So it's not all in terms of Rolang expressions. When we put things in a giant hash table, right, then we affect this associativity, right? Because the hash table doesn't care about the orders of the entries. It's not necessarily the case that you get ordering. And so when I look something up at a key, right, I just plunked stuff down at the key. There's no symbolic information about that history that's maintained in the hash table. The table access information is not maintained by the table. And as a result, we're getting a lot of this kind of, a lot of these semantic equations for free because of the hash table implementation. Does that make sense?
Yes, yes.
So,
in the same way, how we can use set for storing something and erasing if we are putting multiple elements of the same thing.
Correct. That's exactly right. That's exactly right. If we had a purely symbolic representation, we would be forced to implement something like this or create a translation from the purely symbolic into something like a hash table. But that's in fact exactly, and just goes to show how stupid and how long it takes for me to grasp this kind of stuff. I actually had to go and try out various rewrite implementations of pi and rho and other kinds of concurrency systems before I saw, like, the first thing I did was the tuple space style implementation, and I knew it was efficient, but I didn't understand why. Then I had to go and do implementations in rewrite style and understand, I'm getting all of this extra equational information for free. I'm not having to get the term rewrite system to do it for me. Now, the flip side of that is what we've been talking about today, is that you need to put it back in if you want your bisimulation to catch these structure function relations. Does that make sense?
Yeah. So you're saying that we can use something much simpler, like a hash table for this purpose, and we can add this additional information that we lost by using this like nice structure that we already have.
Yes, that's correct. And again, I'm not suggesting that we compute using associators and identity things. I'm simply saying that if we were to do that, then bisimulation sees everything the logic sees, and all is well in the world, right? What would be really weird is if the logic can see stuff that bisimulation can't see. Right? That's you know, that goes against what we've been learning about bisimulation, as it's somehow the bedrock or the foundation of all of our useful notions of equivalence. Cool. Well, I really appreciate you guys listening to me mumble on about this stuff.
This is super interesting. Thanks.
So, I mean, I'm curious, does logic see the structure somehow that bisimulation does not, as a basic computational paradigm?
No,
I mean,
no, that's what I was
why
just, that's what that's what this last hour has been about, is that logic.
No. But what I'm saying is, why is it that logic is exposing things that bisimulation kind of needs to be given the information to, I guess?
Because you took it out. So
Okay.
here, this is erasure. And because you erased this, because you erased all this stuff, bisimulation can't see it, right? But you didn't entirely take it out. You still left this little trace. And the logic is seeing that little trace, right? And bisimulation can't see that little trace because you didn't put that little trace in your COM rule. If you had put it in your COM rule in a way that bisimulation could see it, then you'd be back in business. But it doesn't happen. So the only way to put it back, how do I say this? So a uniquely identified algorithmic way of putting it back is this approach. That's a uniquely identified way of teaching bisimulation what you erased. That's the idea. Yeah. Cool. Well, thank you so much. So we have a stand up in 1 minute.
Yeah.
So see you there.
See you.
Thank you.
Thanks.